right?
Some things there which they do not define.
All right, a couple of quick announcements while people are settling in. I have to be louder. All right. So a couple of quick things. One, there's a schedule swap tomorrow that's already done on the calendar. So Sasha Zhibadov is lecturing third, and Luca's last lecture will be last tomorrow. Second, Sasha is going to hold an office hour on Zoom, so you can sort of interact with him outside the lectures since he can't be here in person. That's going to be tomorrow morning at 8 to 9. Third, conference services has asked us nicely to not go to lunch tomorrow before 1 p.m. Apparently there's just a crush of other events and people happening, so they'd like you to delay heading over to lunch until 1 if you possibly can. I know you've been doing student talks at lunch, so maybe you could do a few extra talks tomorrow. Would be my suggestion, but just they've asked us please not to show up before 1 p.m.
Tomorrow.
Tomorrow. Today is fine, but tomorrow lunch at 1 p.m. please. All right, and without further ado, I'll turn it back over to Luca.
Great. So let's summarize where we ended up last time. So last time we finished discussing the third puzzle, which is the ADS2 CFD1 correspondence well defined? And we started addressing this puzzle by literally repeating the same thing that Juan and others did in the initial derivation of ADS-CFT. They looked in the near horizon region of a black brane and wrote down an effective field theory in that near horizon region and studied excitations around around that background. So we did the same for ADS2 cross S2. We performed an S-wave reduction for the entire space-time, even outside of the near horizon region. And we found an action of the following form. R here is the Ricci scalar of the 2D metric, and chi is a dilaton field that captures the size of the radial direction, of the area of the radial direction. Now, there's a specific potential that depends on exactly what theory you're studying. We studied Reinster-Nordstrom solutions in Einstein-Maxwell theory. This is the potential that you get in that case. And then we performed an approximation, which is that if we want to take the limit close to the extremality and zoom onto the near horizon region to really understand what happens in ADS2 cross S2, we expanded the dilaton field, units of g Newton, in phi naught. Sorry, this should not be there. In value phi naught, which is just the area at the horizon plus fluctuations. So the way in which you should think about this chi is that it captures the value of the S2 area of the horizon and tells you how S2 evolves as you move through the 2D space-time. Somewhat similar to the moduli that Liam discussed in his lectures. Good. So if you plug this into this action and do an expansion at small deviations from the horizon, so focusing on the near horizon region, you get an action that's linear in phi. And this action is called JD gravity and is an effective field theory for the near horizon region. In principle, you have to keep all other massless fields, and you could do that. But for simplicity, to emphasize the problems with this effective field theory, I just kept the degrees of freedom associated to the metric and to the dilaton. Good. And last time, I believe we stopped by looking at the solution to the variation of that action with respect to phi. Now, this action, in order to have a well-defined variational principle, it needs a boundary term, and you have to specify what boundary conditions it satisfies. But for now, let's ignore that and do something a bit more naive and just write the equations of motion in the bulk, right? Good. So let's assume that the variational principle is well-defined and this variation is 0. So the solution to the variation with respect to phi is very easy. Just r equal minus 2, right, over L2 squared. A reminder, L2 itself was the size of ADS2, sorry, not the size, the curvature scale, the radius of ADS2, which happens to also be equal to the size of the horizon for black holes in flat space, and is equal to Q times L Planck. Good, but for now, in order to simplify the calculation a little bit, I'll just set L2 to 1. Good. So a way of writing the metric for when the Ricci scalar is -2 is we just are describing a patch, at least a patch of ADS2. And the metric in Poincare coordinates takes this form. The more familiar form might be this. And going in the two metrics is pretty simple. You just take t is u plus v over 2, and z is u minus v over 2. So these are the light cone coordinates associated to the Poincare coordinates. And in Poincare coordinates, the boundary of ADS2 is at z equals 0. Which is the same as, just from here, it's the same as u going to v. Okay, so people asked me last time that I took the variation with respect to the dilaton. What happens when we take the variation with respect to the metric? Well, in this case, when you take the variation with respect to the metric, you get an equation of motion involving the dilaton. And I encourage you to derive it by yourself. So homework, derive nabla nu phi minus g mu nu plus squared phi plus g mu nu phi equal to 0. So this is the equation of motion for the dilaton. And if you plug in these coordinates and explicitly write down the covariant derivatives, you can actually solve this equation very explicitly. It has free constants that are not fixed by anything. They're in principle set once we fix the boundary conditions for phi. And in the coordinates u and v, the solution takes the following form. This is the most general solution. It can be written in terms of free constants, a tilde, b tilde, and c tilde. It's a tilde plus b tilde u plus v times c minus c tilde u times v divided by u minus v. So let's think a little bit about, yes?
Can you remind me, the original theory is Einstein-Maxwell theory. When you reduce down the near horizon region, you have only pure gravity. So where does it?
Yeah, so there's additional excitations coming from the gauge field and the U1 gauge field that existed in higher dimensions and the SU2 gauge field that came from the dimensional reduction itself. They're in principle captured by these fluctuations. But once we fix the charge and the angular momentum of the black hole, what essentially happens is that if you integrate out those degrees of freedom, you just fix the value of the potential, u of chi as a function of q, the charge of the black hole and the angular momentum of the black hole. So you could either integrate them out or keep track of them, expand your gauge fields around a certain background and see what happens. Keeping track of those gauge fields is important to understand, for instance, the quantization of the charge and the quantization of the angular momentum of the black hole. Yeah. No. Z equals 0 is the boundary of ADS2. It's the edge of the near horizon region. For now, we're just describing this ADS2 geometry and seeing what this action implies.
So where does that fit into your throat picture? Is it like towards the opening?
Yeah, towards the opening of the throat. Yeah.
So the Poincare patch only covers half of the ADS2.
That's right. Yeah. Well, you could write global ADS. The Poincaré patch only covers half of ADS2. That is correct. It's just a choice of coordinate system that covers half of the space-time. If you want a complete description of the space-time, you could work in global ADS coordinates. It's not a problem. You get it's just a choice of coordinate system. Great. Let's try to think about whether A tilde, B tilde, and C tilde can be fixed using the symmetries of ADS2. So for instance, I could choose, I could do, ADS2 has an isometry, which is the same as the 1D conformal group. It's SL2R. And this isometry acts on U and V by sending U and V to AU plus B over CU plus D, and V to AV plus B over CV plus D, where this matrix A, B, C, D is a matrix of real numbers with determinant 1. That's what SL2R, how SL2R can be described. Good. If you plug these two transformations into the metric there, you could check, do this in Mathematica, you could check that the metric is invariant. Great. So you could do this transformation on phi itself, and what you'll find is that the value of B tilde changes under this transformation. The value of C tilde can change by a multiplicative constant, but not as important. So using these transformations, we have the power we can set B tilde equal 0. Now, A tilde and C tilde are thus undetermined. The only thing that determines them is the boundary conditions at infinity, are the boundary conditions at infinity. Well, let's try to get some inspiration from ADS-CFT. In ADS-CFT in higher dimensions, we don't like when a field diverges as it approaches the boundary. Yeah.
So why do you want to insert the full isometry of the solution?
What do you mean? This is an isometry of the solution. I'm just doing a transformation that gets rid of one of these constants. So I'm just trying to write the most general solution. After I do a symmetry transformation, the statement is that I can fix one of these constants to 0. So physically, I only care about two of these constants.
Right, okay.
Good.
Just moving blocks into the center.
Exactly. Yeah. So good. So now, yes. Yeah. Yeah, it's not invariant under the SL2R transformations. Yes, yes. That's a good point, and that will be very important. Yeah. So yeah, maybe one way of saying it is if you want to actually preserve the symmetry, the SL2R symmetry fully, the only option is to set A tilde and C tilde to 0. Now, you could try to preserve the symmetry. Yeah, so let's go back to what people typically do in ADS-CFT. In ADS-CFT, people try to put boundary conditions at the boundary of ADS such that all fields decay at the boundary of ADS. So you could try to do that here, but you see that if you take A tilde and C tilde to be different than 0, then this field phi actually diverges at the boundary of ADS. The boundary of ADS is Z going to 0 or U going to V, and because of this denominator that goes like 1 over U minus V, you get a divergence. So if you want the standard boundary conditions that are taken from higher dimensional ADS, if you want to fully preserve the SL2R isometry, you would have to set A equal B tilde equal C tilde equal 0. So this just describes really an ADS2 geometry with a constant S2. No problem. But now the issue arises when we consider excitations around these solutions. So let's take this solution that has these boundary conditions and put in a particle. So let's couple the theory to, let's say, a free massless scalar, a 2D CFT. If you do that, then so couple theory to matter. Yeah.
Sorry, can you explain again what boundary conditions we're picking here?
So at,
Combination of A, B, C that do respect the Poincare-Patch isometries, right?
sorry?
There is one combination of A, B, and C tilde that respect the Poincare.
So here we're just imposing that the field decays to 0 at the boundary, that it's not divergent. Yeah.
Okay.
That sets A tilde equal B tilde equal C tilde to 0, and there's basically a unique option. Yes. So we can couple the theory to matter. And if we couple the theory, the matter only to the metric and not to the dilaton, we get no change for the equation of motion that comes from the variation of the action with respect to the dilaton, but the variation of the action with respect to the metric does change. So di dg mu nu equals 0. Is this big enough? No, okay. Now implies delta mu, delta nu, phi, minus g mu nu, nabla squared phi, plus g mu nu phi, is equal to minus 8 pi g Newton in d equal 2 t mu nu. Great. And again, using the fact that I'm just describing a theory in rigid ADS2, the solution to the metric is the same. You could plug that solution to the metric to write down explicitly this differential equation. And we could explicitly write down the solution to the differential equation, which looks quite similar to what I wrote over there, but in the presence of an arbitrary stress tensor. Great. So the solution, again, can be described in terms of the coordinates u and v, and takes, again, the form a over u minus v times 1 minus c over a times uv minus 8 pi g Newton over a times I plus I minus, where I plus and I minus are integrals of the stress tensor along the direction of null geodesic. So this I plus depends on u and v, and it's an integral of the stress tensor along null direction, which we parameterize by s. And this an integral is from u to infinity. And there's a similar formula for I minus. It's the integral from minus infinity to v ds s minus u s minus v tvv of s. Good. So here the stress tensor TUU depends on u, and TVV depends on v. So let's consider some pulse sent in from the boundary of ADS2 into the bulk. Let's assume that it's a relativistic shock wave that we send in. So we can send in a relativistic particle from the boundary at t equals 0 and z equals 0.
Look at the 2D G Newton is related to the 4D G Newton by some fine art.
Yes, yes. Yes. That's why, yeah. Is the matter conformal? Yes. Okay. So if we send in such a pulse, then there's a profile for the stress tensor that just looks like a delta function. So TVV as a function of v just looks like epsilon times delta of v. In Poincare coordinates, if I were to draw what the patch of ADS2 that's covered by Poincare coordinates, this is the boundary of ADS2, where z goes to 0. And as we established, we want the dilaton to go to 0. And at this point, we send in a particle that moves along a null geodesic. And along here, so this is the u direction, and this is the v direction. And along the v direction, this is basically like a delta function. So let's see what happens if I plug this into I plus and I minus. Well, the only term that I get will be in I minus, because I don't turn on anything for TUU. Should I continue here? Is that okay? So if you do that integral for I minus, you get a theta function, right? So the integral of a delta function, you plug it in here. The delta function only activates if v is greater than 0. So you get a theta function in v. So I minus is the coefficient of the delta function, which captures the energy of the particle that I'm sending in, times uv. That comes from the two terms appearing in the integrand, times a delta function in v. Sorry, a theta function in v. Okay, so let's plug this in the solution for phi. So generally, the solution for phi will now be a over u minus v times 1 minus c over a times uv plus 8 pi g Newton over a times I minus, which is e times u v theta of v. Okay, so what do we observe? Let's say that we wanted the dilaton field to be 0 before I sent in the particle, right? I set it to 0 before. This implies that when I'm taking negative values of v, this term is not here. So this implies, as we concluded before, that a and c have to be 0 as well.
Luca, I don't know if it matters, but I think you have a sign difference on the last term from.
Yes, you are correct. There's a minus sign here. Thank you. Great. So we initially set a and c equals 0, but now we see that we run into a problem. What's the problem if E is non-zero? E could be arbitrarily small, an arbitrarily small perturbation to the space-time. Well, the problem is that if I set this term to 0, and I multiply this term by this term, I end up with 8 pi g Newton divided by u minus v. Good. D equal 2. Good. Times E u v theta of v. So you see, I tried to make the dilaton not divergent before I sent in the shock, and I send in an arbitrarily small matter perturbation, and all of a sudden my dilaton afterwards blows up at the boundary of ADS2. This is something that doesn't happen in ADS5 cross S5. If I send in a particle from the boundary of ADS5 into the bulk, I don't see the size of S5 being back reacted on and completely change after I insert that particle. So the issue with ADS2 that Polchinski and Almiri noticed a while back is that it's very prone to back reaction. So back reaction destroys the ADS2 solution that is SL2R invariant. Good. So now let's relax this assumption that phi needs to go to 0 at infinity. If I relax that and I am OK with breaking the SL2R isometry, then I might as well take phi to go to infinity both in the past of where the particle is inserted and in the future of where the particle is inserted. And if I do that, if I act with a small shock, if I set A to not be equal to 0, then indeed the ratio between phi after I insert the particle and phi before I insert the particle could go to 0 as E goes to 0. So what all this is instructing us is that we have to change the boundary conditions for phi in order to make sense of this as a theory in ADS2. By changing these boundary conditions, as one of your colleagues pointed out, forces us to break the SL2R isometry of the spacetime explicitly. Now the spacetime is no longer homogeneous. Rather, this dilaton field varies depending on which point in the spacetime I'm at. So let's see how this fits into the analysis of the black holes, the Reinstein-Nordström black holes that we were discussing earlier. So for that, I'll start with a black hole that has a tiny temperature, T, and see what happens. Yeah. So, sorry, I couldn't hear.
Could we have kept more of the notes that we threw out when we were doing the dimensional reduction, and how would that have affected this?
It wouldn't have. So we could look at the solution where all those modes are turned off, where I turn off any fluctuation on top of the flux, electric or magnetic flux that I turn on, or and in which I turn off the SU2 gauge field that appears in the dimensional reduction. And similarly, I can turn off any other scalar field. And I still can just consider an excitation of this scalar field. By the way, this conclusion is generic. It doesn't depend on the fact that I took a 2D free scalar and conformally coupled it. You could, while you might not be able to explicitly solve the equations of motion for phi of u and v, you'll still get the conclusion that if you start with phi going to 0 at infinity and put an arbitrarily small perturbation, after the insertion of the perturbation, you're forced to take phi going to infinity. Great. So let's try to deduce what the natural boundary conditions are if we start with a black hole, a Reinstein-Nordström black hole. I drew a spatial slice of this Reinstein-Nordström black hole last time. Let's try to deduce what the natural boundary conditions are at the edge of the ADS2 throat when I now keep a small but finite temperature for the black hole. So I'll fix beta at infinity. Here, when beta is sufficiently large, namely when it's larger, much larger than Q, the near horizon region has an ADS2 times S2 approximation. And I can write that EFT in a region where the ADS2 cross S2 approximation is good. And let's say that I cut off, just like in ADS-CFT, the region where the ADS2 cross S2 approximation is good at some cutoff that I'll symbolize by this yellow line. So the question is, given the boundary conditions that we impose at infinity, where we fix the temperature beta, and the value of, let's say, the electric field and so on, what boundary conditions should I fix here? And at this point, we'll analyze the variational principle for this effective field theory, the JT theory, in a bit more detail. So in the near horizon region, in the near horizon region, the black hole looks like the geometry looks like AdS2 cross S2. And out of this region, it basically doesn't make a difference that I turned on beta, with the exception of the periodicity of the tau circle. Locally, the metric still looks like the metric of an extremo black hole. So in order to figure out these boundary conditions, we can expand the metric outside of this near horizon region into the extremo metric plus some perturbation. Good. And I can integrate, and similarly chi can be expanded into chi in the extremal geometry plus some perturbation delta chi. So now I can write now I'm interested in writing the total action as a function of the action in the near horizon region plus some other terms that are constant plus a possible boundary term that appears on the edge between AdS2 cross S2 and the region outside of the near horizon region of the black hole. So if I do that and I integrate by parts these fluctuations on the outside of the near horizon region, what you get is that you get an action that's evaluated far away, in the far away region from the near horizon region, on the extremal metric, plus the action in the near horizon region, plus a boundary term that comes from the integral by parts of these modes. And the boundary term looks like minus 1 over 2g Newton, integral over the yellow boundary, du square root of h times chi delta k minus derivative along the normal direction of chi, the normal direction to this boundary of chi, minus chi times k times the change in the metric between the inside and the outside of this yellow region.
Can I ask?
Yeah.
So this I total is now, you've done the perturbation and then dimensionally reduced also?
Yeah, so I've done the perturbation dimensionally reduced. This is the total action. I wrote down what the action in terms of chi and g was. That's the total action still. And now the only thing I'm doing is I'm trying to focus on the near horizon region by essentially integrating out the dynamics outside of the near horizon region, expanding the metric outside of the near horizon region into the extremal metric plus a fluctuation, and then integrating things by parts to essentially isolate all the dynamics and the geometry to this near horizon region plus this boundary term. Yeah, it's still a 2D metric that's evaluated at extremality. Yeah.
So, sorry, maybe I missed something over there. The energy is defined at the boundary, right? Very, very far of the particle.
The energy at the boundary of AdS2.
Far away from the extreme black hole. So, would there be a redshift factor that could compensate and help us in the case where A equals to C equals to 0? When I go close to the black hole?
I don't believe so, but maybe we can talk about that afterwards. Namely, I think the stress tensor in these coordinates yeah, will not receive.
The orthonormal coordinates, then it should be okay.
Yeah. I don't think there is a compensating factor. Yes. It's a change in square root of the induced metric along the yellow line. Yeah. So suppose that we define the edge of this Froth region as a location where we fix the induced metric. So we fix HUU. And we fix the size of the S2. This is the definition of the region where I separate the near horizon from the faraway region. If I do that, then delta of square root of h, the variation of the metric at that location, is just 0. So this term drops out. Good. So this, if I fix the induced metric at that location, this also implies that in 2 dimensions, I fix the proper length of the curve that sits on this yellow region. Namely, if I take square root of h to be the total, to be some L over epsilon, where L is the integral over dt square root of h tau tau, dt square root of h tau tau. This is beta L2 over the redshift factor epsilon. I can write this explicitly out as beta L2 times r tilde boundary. Remember that the metric expanded, I expanded the metric in the near horizon region in terms of a radial coordinate r tilde. And I can take an r tilde which sits at some location 1 over epsilon. The length, the proper length of the separation region is fixed as a function of the inverse temperature beta, the radius of ADS2, and the radial point where I choose to separate my near horizon region from the rest of the space-time. Good. Now, we can similarly solve for, given what the induced metric is on this curve, we could also solve for what the dilaton is at this location by solving the equations of motion outside of the near horizon region. So we just look at this extremal metric and look at what the extremal value of the dilaton needs to be at a location where the induced metric takes this form. And what one finds is that the value of the dilaton on the yellow boundary is given by 2q cubed times r tilde boundary. This just follows from the fact that chi over g Newton was written as phi naught plus phi, and chi as a function of r tilde was just q plus r tilde boundary, q squared, everything squared. So at leading order in r tilde boundary, I get that the value of phi is set by r tilde boundary times 2q cubed. Okay, so this is what sets the value of the dilaton. This is what sets the value of the induced metric. And notice here that r tilde boundary is somewhat of an arbitrary choice. I can move my boundary further, my boundary of the near horizon region further and further, and I might still be in the ADS2 cross S2 region. So all physical answers should, at the end of the day, be independent of what this r tilde boundary is. And we'll see that that will indeed be the case. But assuming that, the only dimensionless ratio that I can form from these two quantities that gets rid of r tilde boundary or gets rid of the cutoff scale epsilon comes from the ratio between the two. Namely, if I take the total proper length of the boundary that's represented by the yellow slice over there, and I divide it by the value of the dilaton times L2 to form a dimensionless quantity. What you get is m Planck over q cubed times t, which is the same as m breakdown over t. Here I restored the units of m Planck to make the comparison with m breakdown more clear. So essentially, what's m breakdown divided by t, m Planck over q cubed t, of the length divided by the value of the dilaton at the boundary. The value of the length of the boundary divided by the value of the dilaton at the boundary. Yes. It's square root of h tau tau divided by phi. So this is the physical parameter. If we'll indeed check that everything is independent of where I choose the cutoff, but this is the physical parameter that controls how my theory behaves. And we all already noticed something very interesting, which is this physical parameter is exactly what controls how close to the breakdown scale the theory is. And we'll see that this ratio will play an important role in a second. So in order to proceed, let's continue by just evaluating the action that I wrote here explicitly using these boundary conditions. I now have a well-defined variational problem where I'm fixing the metric at the boundary of ADS2. I'm fixing the value of the dilaton. It's not 0. Rather, in terms of the temperature, it could be the ratio between the dilaton and the temperature could, in principle, be a very large number. So I can now evaluate what this total action is by looking at the solution for the effective field theory in the near horizon region, and then explicitly evaluating this term outside of the near horizon region that just evaluates to a constant. Yes?
I thought R tilde was large. Is that the case?
So R tilde is, I think, carries units. It's large compared to square root of m.
So this expansion
Times m Planck.
the boundary value for the time we look at medium order and R tilde. Is that
Yes, so this is much larger than this. But when you compare the value of R tilde compared to the temperature scale, the value of R tilde can be much larger. Yeah.
So just to clarify, as compared to what we did before, that you only just took the action in the near horizon region, but now you got like a fixed action by using the equation motion to integrate out the metric perturbation in the far away.
Mm-hmm. Yes. So the action in the near horizon region remains the same. I just don't want to deal with the dynamics that can occur outside of this near horizon region. And integrating the metric in the near horizon region looks arbitrarily close to the extremal metric if I go at low temperatures. So I just integrated the possible changes in the metric by parts to rewrite that as a boundary term at the edge of the near horizon region.
Also, right?
Outside of the near horizon region, yes. Yes.
Yes.
Yes.
Boundary term is coming from the by parts they're far away option, right? So the near horizon also has boundary terms.
No, so the near horizon is as it is. It was just an approximation to the entire action in the near horizon region. And then I just integrated. So in principle, I could have written my original action just as a function of chi and g. But I didn't do that. I chose to separate the near horizon region and do an integral by parts in the far away region using the equation of motion to get this boundary term that is now a boundary term at the edge of the near horizon region. So this delta k is the difference between the k in the near horizon region, the extrinsic curvature on the boundary of the near horizon region, so measured with respect to this normal vector, minus the k on the outside region after I did the integral by parts. And the k on the outside region after one does the integral by parts turns out to be 1 over L2. You could explicitly calculate it because you know the geometry outside of the near horizon region exactly. Great. Good. So we can evaluate this term explicitly. This term will just give us something proportional to beta, something equal to beta q. And we can now, we're now left with an action that just depends on this near horizon region term and this boundary term for the near horizon region. So the effective field theory that I get that captures all the dynamical degrees of freedom is just I NHR plus this term. And this is a very simple theory. If, for instance, I sum up, this chi can be written as phi naught plus phi, chi over g Newton. So the factors of g Newton cancel. So there's a term in here that depends on phi naught and a term here that depends on phi. The term that depends on phi naught is responsible for producing the extremal entropy term in the on-shell action. So if I collect all the terms that depend on phi naught from the near horizon region action and from here, I get phi naught over 2 pi times 1 over 2 integral of square root gr plus integral of square root h times k. And this you might recognize as the Euler characteristic as 4 pi. This formula is the formula for 4 pi times the Euler characteristic of the 2D spacetime M. Since the spacetime that I'm studying, if I'm in Euclidean signature, since the spacetime that I'm studying has the topology of a disk, in 2D, this chi just evaluates to 1. So this term in total just gives phi naught, which was the extremal entropy of the black hole. So now the only leftover term is the term that contains phi here and the associated term that contains phi on the boundary. Remember, phi is fixed at the boundary, but it still appears in the boundary term. But for that, I can, if I'm just interested in the on-shell action, or if I integrate out phi explicitly, R is set to minus 2 over L2 squared. So the metric is indeed just that of ADS2 in the near horizon region, exactly after integrating out phi. So I could write it in Poincare coordinates as ds squared being dz squared plus dt squared over z squared. And what I'm left with is simply this boundary term that contains k evaluated at the edge of the near horizon region. So after inserting this in the JT gravity action, one gets that the total action is given by beta times the extremal mass, which is just beta times q, minus S naught, the term that came from the parts of the action that were proportional to phi naught. I'll call phi naught is the same as this S naught, and it's the extremal entropy, minus the boundary term evaluated on the yellow curve, which is 1/2 integral over yellow du square root of h phi at the boundary times k in the near horizon region minus 1 over L2. Great. So the entire action in the entire space-time, if I just focus on the S-wave sector and integrate out all the other massless free fields that I get from higher dimensions, like the gauge field, the U1 gauge field, and the SU2 gauge field, the entire action just reduces to this boundary term evaluated on the yellow curve. So we're just describing locally, we're just describing an ADS2 space-time where we're fixing the boundary to have a very large, we're fixing a patch of the ADS2 spacetime that describes the near horizon region. And the proper length of the boundary of that patch can be very large. So if I draw this in Poincare coordinates, this is Z, this is T. I'm describing some patch of these Poincare coordinates with the boundary being very large in terms in ADS2 units. A boundary being large is only possible if part of the boundary of this patch gets close to Z equals 0. This is because the closer I am to Z equals 0, the larger the induced metric on this boundary is. So the boundary curve, this boundary curve of the near horizon region is described in terms of a curve in Poincare coordinates as a function of some affine time u that parametrizes time on the boundary. Or sorry, let me call it tau first. And we can take tau to be periodic Sorry?
This boundary curve, is it related to the yellow line?
Yeah, yes, so the boundary curve is in the tau z plane. This yellow line, I drew it at a fixed tau. So how you should think about it is that you also have time, the time direction. The time direction is periodic. There's the yellow line represents a point in the Poincare plane. This yellow line represents a single point because we're fixing the time. So it's just, yeah, the points, I should have drawn that in yellow, but a point on that yellow line is a point on this plot, is this line on this plot. Yes?
So this derivation we've like learned how to take care of the boundary terms like from the original theory.
Mm-hmm.
Could we have just started from the get-go with general gravity and like perform like give us one theoretic procedure of taking the boundary terms?
You could have done that. The reason why I chose to do this is to show how the boundary term appears on this yellow curve or red curve, as I drew it here, by integrating changes in the metric in the faraway region. Otherwise, like you could include that boundary term sort of by hand, but you know, this is the actual reason to include it. Yeah.
As we take the cutoff away, is the value of phi on the boundary becoming large compared to the phi 0?
As we take epsilon to 0,
Yes.
is the value of
Phi b becoming large compared to phi 0?
No, we could still work in a regime where phi b is much smaller than phi 0, but much larger than you know, the ADS scale, which is the ADS2 scale, which is the important scale to be concerned about. Great, because notice that the ADS2 scale goes like q, right? The phi naught goes like q squared. So there's a regime in between q and q squared that's very large.
So if you choose flat, then I'm recovering the result from the first lecture, or
Flat.
it's like a total until action. Like for some configuration, are we supposed to get the result we started with, right? When you
Yeah, it turns out that a flat line in these coordinates actually has an action that depends on the time t. And the result will be that this will actually look like a very large circle.
right. I was just wondering how to get back the result we started with, like where we didn't have a metric perturbation.
Sorry, this will turn out to be the result without a metric perturbation. The confusing thing is that we have to change between the tz coordinates and the r tilde t coordinates that we discussed previously. And the change is more complicated and maps a curve of constant t in those coordinates, constant little tau in those coordinates. Sorry, constant little r and variable tau onto a curve in the tz coordinates, that is a circle. Does that? Okay. Good. So we're trying to describe things as a function of t of tau and z of tau. And we can write the induced metric as a function of t of tau and z of tau. So the induced metric, h tau tau, needs to go like 1 over epsilon. If I set the periodicity of tau to be 1 over epsilon L2, I believe. If I set the periodicity of tau to be beta, and this implies writing the induced metric explicitly in terms of t of tau and z of tau implies that L2 squared divided by epsilon squared is z prime squared plus t prime squared over z squared. Good. So from this, you can indeed see that in order, if I want this epsilon to be L2 over epsilon to be very small, very large, the only option is to keep z very close to the boundary. So solving this in a perturbative and expansion in epsilon, one finds that z is equal to epsilon over L2 t prime, plus higher orders in epsilon.
All these primes are tau derivatives.
Yeah, all these primes, z prime and t prime, are dz of tau, d tau, and the same here, dt of tau, d tau. Perfect. So, I thought I mentioned it, but I forgot to write it down, or maybe I forgot to mention it. I am setting the periodicity of tau to be by convention beta. And the fact that I can fix the induced metric locally to take this form follows from the fact that the proper length of this curve is beta L2 over epsilon. So that's my convention for tau. Great. So the only thing I have to do in order to evaluate this action as a function of this curve, t and z, is see what the extrinsic curvature at the boundary of ADS2 is as a function of these coordinates. And that can be computed very explicitly. It turns out to be t prime times t prime squared plus z prime squared plus z double prime minus z prime t double prime over t prime squared plus z prime squared to the power 3/2. Again, you could do this in Mathematica. The DFO package can actually evaluate extrinsic curvatures. You're just asked to evaluate the extrinsic curvature of a curve in ADS2 that has this arbitrary form. So now we can plug in the solution for z from here and here. And now we can write the extrinsic curvature at the boundary of the near horizon region only as a function of t. So we're essentially integrating out z and we're going to obtain an action that only depends on t of tau. And the action, plugging in this equation and expanding again in epsilon, is that k at the near horizon region is 1 over L2 times 1 plus epsilon squared an object called the Schwarzian derivative of t with respect to tau, plus higher terms in epsilon. So at leading order, the extrinsic curvature is just close to 1 over L2. And there's a subleading order that fluctuates. Good. The curve that has k exactly equal to 1 over L2, by the way, is the curve that has z equals 0. The boundary of ADS itself has this extrinsic curvature. Great. Yeah. So is there something that we're doing to all the derivatives of z?
Well, when we do z goes like z prime to first order.
Uh-huh. Yes, which follows from this, self-consistently it follows from this equation, right? Because I can take the derivative of z. This is a functional equation. It's true at any point. So I can take the derivative of z at any location and find that z prime is epsilon t double prime. So then you could plug, you essentially do need that because you have z double prime in here. You plug in both the value of z, the value of z prime, and the value of z double prime in this equation, and you get this expression that depends on the Schwarzian derivative. The Schwarzian derivative of t and tau is equal to t triple prime over t prime minus 3/2 t double prime over t prime squared. Now, the reason why you get such high derivative orders is precisely because you have to plug in what z double prime is as a functional of t. So essentially, we've reduced, yes?
I was just going to ask, can you make any comment on the physicality of what the Schwarzian derivative is, or is it just the thing that comes out?
Yeah, I was going to say that now. Yeah. So essentially, we've reduced the entire action, the entire effective action, to a boundary term that's evaluated on a curve, and the weight of different curves is just given by this Schwarzian derivative. Now, you could ask whether one can derive this effective field theory a priori just based on symmetry reasons. The physical way to think about this Schwarzian derivative is that it appears precisely because we set the value of the dilaton, the value of the dilaton phi, the variation of chi compared to the near horizon region, to be non-zero, right? And the fact that we set phi to be non-zero at the boundary of ADS2 explicitly broke the SL2R isometry of ADS2. And the way in which one can think about this Schwarzian derivative is that it's the EFT for the breaking of SL2R, and this mode T is like the Goldstone mode for the breaking of SL2R. Now, one thing to check is that in a theory of Goldstone modes, one should check that the action of the Goldstone modes itself has the symmetry associated to, has global symmetry associated to the symmetry that was broken, namely that Schwarzian has an SL2R symmetry, and indeed the Schwarzian has an SL2R symmetry. Which sends t to AT plus B over CT plus D. So So if I take T prime, T tilde to be this combination, one can show that the Schwarzian of T tilde comma tau is the same as the Schwarzian of T comma tau. Yes?
I'm a bit confused by this. So I thought that like Iliesiu is breaking SN2R explicitly. So the Schwarzian is Iliesiu is the whatever the action for Iliesiu to Goldstone boson. So that should be invariant not under the full SN2R, but the group that Iliesiu breaks down the SN2R to.
SL2R?
SN2R is going to something, right?
Yeah, I think here, given boundary shape, right, general boundary curve, T and Z, and given the profile of the dilaton, the entire SL2R subgroup is broken. Now, the action of the Goldstone mode for that breaking is still invariant under the original symmetry. You mean why don't we expect a Goldstone for each generator of the SL2R? Well, I think in some sense this just follows from the, yeah, let me delay that question a little bit. Yeah, perhaps there is a way to rewrite there's different ways of rewriting the Schwarzian derivatives by integrating in fields. Which can make it more explicit that there's a field corresponding to each generator. But the main thing that you should check is that the effective action that you get is invariant under the symmetry transformation. OK, so we obtained this action. We analyzed its symmetries. We can also analyze its coupling. Now, if I plug in what this K in the near horizon region is into the total action, one finds that the total action is beta times m naught minus s naught minus phi r divided by 2 integral from 0 to beta dt times the Schwarzian of t and tau. So two things to notice. One is that this factor of 1, I don't know if I still have the total action written down, but if you have it in your notes, oh yeah, here it is. That factor of 1 in the near horizon region precisely cancels with this additional term that comes from evaluating the extrinsic curvature on the outside region. That's number 1. Number 2 is that there's a factor of epsilon squared sitting in front of the Schwarzian in the extrinsic curvature. That factor of epsilon precisely cancels with the factors of epsilon that you encounter in square root of h and in the value of chi at the boundary. So square root of h went like 1 over epsilon. Phi at the boundary also goes like 1 over epsilon. So at the end of the day, we obtain an action that is completely independent of where we took the cutoff between the ADS2 cross S2 and faraway regions. And this factor of phi r over 2, using what I wrote over there, can simply be written as 1 over m breakdown. Great. So what is the coupling of this theory? Naively, you would say that I have an action whose coupling is given by 1 over m breakdown. However, that's a little bit not quite right. There is also a factor of beta appearing in the action. And one can actually can combine the factor of beta with the factor of m breakdown using the following trick. If I redefine tau to be some different affine time u times beta, such that now u is periodic with unit period, then you could study how the Schwarzian transforms under this transformation. The Schwarzian of T u comma u turns out to be exactly equal to 1 over beta squared, the Schwarzian of t tau comma tau. You could almost immediately see how that follows. It follows from the fact that if I track the if after a rescaling I track the number of derivatives in the numerator and denominator, I get a factor of 1 over the rescaling factor squared. So plugging this into the action, I can write an action that is now completely independent of beta. Sorry, it's Schwarzian of t of u. Great. So here, the integral of this action is from 0 to 1. I've isolated the factor of m breakdown and the factor of beta from the rest of the action. And I see that the effective of this action is not 1 over m breakdown, but is instead the ratio between the temperature and m breakdown itself, which was related to the ratio between the proper length and the boundary and the value of the dilaton at the boundary. So why is this important? Why is this effective coupling important? Well, let's say, notice that I've reduced my initial action that had factors of g Newton to this simple action in which the coupling is now just given by this t over m breakdown. So I can decide whether or not my action has a mode that's strongly coupled or not. And based on that, I can decide whether it's correct to do a saddle point approximation for my action or not. It's only correct to do a saddle point approximation for a given action if there's a large factor multiplying that given action. So when t over m breakdown is large, saddle point approximation is okay. But when t over m breakdown becomes of order 1, the classical configurations no longer dominate. And I need to care about the quantum fluctuations of this mode t of tau that parametrizes how the near horizon of the geometry is glued to the faraway region. So let's start with the regime where t over m breakdown is much larger than 1. That'll take 3 minutes. Is that OK? And maybe I'll answer the questions at the end. So saddle point. When I take the saddle point approximation, I have to look at the variation of the action with respect to t. This is my field. Now, do you guys know how to take the variation of the action of an action that has very high derivative order? Maybe you don't, maybe you do, maybe you don't. You could try to rederive the Euler-Lagrange equations. And if you, for a Lagrangian that has higher derivative terms, the equation of motion looks like dl d tau. Sorry, the Euler-Lagrange equation looks like dl d tau, d du, dl d t prime, plus d squared du squared, d squared l d, sorry, dl dt double prime, minus d squared d, sorry, d cubed du cubed dl dt triple prime, this is equal to 0. If you have, I stopped here because the action itself has terms up to third derivative order, because the Schwarzian has terms up to third derivative order. But in principle, if you had an even higher derivative action, just include more and more terms. Okay, and this equation of motion can be very neatly rewritten as the derivative of u of the Schwarzian itself is equal to 0. You could show this explicitly by plugging in the Schwarzian as your Lagrangian, which implies that we need to look at configurations for which the Schwarzian is a constant. Or configurations for which the extrinsic curvature in the near horizon region, the fact that the Schwarzian is a constant implies that the extrinsic curvature in the near horizon region is also a constant. Now, you could solve again explicitly for the configurations in which the Schwarzian is a constant. And what you get is that if you impose this periodicity condition that u is periodically identified, then the solution is that T of u goes like tan of pi u. And plugging that into the Schwarzian action, you find that the integral from 0 to 1 of du, the Schwarzian of u, the Schwarzian is just a constant, Schwarzian of T of u, comma u. So we just integrate this constant from 0 to 1. This ends up, the constant ends up being 2 pi squared if you plug this specific function. And you get that this is 2 pi squared and breakdown inverse beta inverse. Plugging this into the total action, we get beta times m naught minus s naught minus 2 pi squared divided by beta and breakdown. Now, I encourage you to go back and look at the free energy that we derived for a near extremal black hole. And this is precisely what we got before. This confirms that when we do the saddle point equation, that when we look at the saddle point for the integral over this Schwarzian mode, we're essentially reproducing our old free energy in the semi-classical limit for a near extremal black hole up to leading order in beta. The advantage of doing all this is that now we could study the other limit. Sorry, it's here. The limit when quantum corrections become important and the classical configurations no longer dominate. So essentially, what we've isolated through this calculation are a set of modes of the metric, of the original metric, that have large quantum fluctuations, while all the other modes of the metric that are not included in this S-wave approximation have a suppression that goes like 1 over the ADS scale. It's a completely different suppression than the ratio between T and M breakdown. Okay, I will stop here and take a few questions.
Well, we're a few minutes over, so maybe one question max.
Sorry, I want to go back to the boundary condition, because it seems like the scaling of z with t prime and epsilon is sufficient to satisfy the boundary condition, but it doesn't seem obviously necessary.
It doesn't seem necessary. Ah, okay, let me rewrite it. It's okay. I'll be quick. So we took 1 over epsilon squared to be z prime squared plus t prime squared over z squared. And we're taking, well, there's L2 squared over epsilon, and we're taking L2 over epsilon to go to infinity. Good.
Small z and order 1z prime.
Small z. So you want small z everywhere and order 1z prime. Well, if we assume that z is small, then indeed we derive this equation, right, which is z is equal to epsilon over L2 t prime, which is it's a functional equation. It's true for any u or any tau. So I move z to the other side, right? Move epsilon to the other side. Assume that z prime is small. Solve this explicitly. And then check whether indeed it's true that the assumption that I made is correct, right? So you plug this, so you take another derivative here, you get z prime is equal to epsilon t double prime over L2. So that confirms that it's correct. Yeah, maybe you're worried that one might not need to make this assumption.
Since we're getting a little over, why don't we?
Yeah, okay.
Let's thank Luca again.
All right, quick announcement.